Hi, my name is Darian Hirotsu, and welcome to our NEC Software Defined Networking Technical Deep Dive series. In this video, we'll cover an 802.1x and OpenFlow network integration use case. As network engineers and security engineers, we're constantly challenged with enforcing security policy across disparate devices while also simplifying network operational tasks. This video is for technologists looking to implement network access control using 802.1x and OpenFlow featuring NEC's programmable flow. Here we'll cover our 802.1x and OpenFlow integration scenario in 6 steps. This first video shall cover the first 4 bullets illustrated in bold. We'll start by discussing different authentication methods available with Radius so you can plan your Radius deployment. Next, we'll go over different use case scenarios for DHCP server homing, which will allow you to plan where to place DHCP servers, as well as DHCP relay agents. Next, we'll cover the network access control implementation details for the wired scenario, including logical diagrams, the wired LAN authentication steps showing the packet walkthrough, a sample VTN configuration so you can replicate the scenario, and lastly, a physical diagram. We'll conclude this video with a demo of the wired 802.1x and OpenFlow integration use case, and we'll follow up on an additional video so you can see the same scenario for a wireless use case. First though, let's discuss different authentication methods available with Radius. There are a handful of authentication methods supported by Radius. First, we'll cover plain MAC authentication. In this scenario, hosts don't support the 802.1x protocol, so MAC addresses must be known and configured in the Radius server beforehand so users may get access to network resources. The second scenario is where either 802.1x or MAC authentication may be used, and this scenario is pertinent when some hosts have an 802.1x client and others don't. Thirdly, is the scenario where 802.1x clients must also use MAC authentication. In this scenario, both the MAC address and 802.1x credentials are checked against the Radius server. In this scenario, this line is highlighted because this is what we'll show in the demo coming up shortly. And finally is the scenario where we'll use web authentication and MAC authentication, which should be considered for a scenario such as wireless guest access. Next, we'll talk about DHCP server and use cases. In both the wired and wireless network use cases, 2 options exist for DHCP server homing. In option 1 for the wired scenario, the DHCP server may reside in the legacy network, meaning it would home to a traditional networking device. In option 2, the DHCP server may reside in the OpenFlow network, which is what we'll demo coming up. For the wireless scenario, 2 options again exist. First, the DHCP server may be an access point or wireless LAN controller. This is again what we'll demo. And secondly, the DHCP server may also reside as a separate machine in, say, the OpenFlow network. In this next slide, we'll dive into the details of the 802.1x and OpenFlow network integration. To illustrate the 802.1x and OpenFlow integration, we're showing a mapping of virtual networks to the physical topology. Starting at the bottom, we'll discuss the physical topology, and we'll start by illustrating the 802.1x authenticator provided by a traditional network switch. In this scenario, recall that the Radius server homes to the traditional network. The traditional 802.1x switch has an uplink configured as a trunk port into the NEC programmable flow or OpenFlow network. The programmable flow network is configured and cabled as a spine leaf representing a campus fabric. Also note to the bottom right, we have a series of data center resources, including an NFS and a web server. Also, the DHCP servers home here and are providing IP addresses to our corporate users. Moving up to the virtual diagram, we're showing a series of virtual tenant networks, or VTNs, to illustrate how the physical topology can be sliced into different virtual tenant networks. Users that are correctly authenticated via Radius are mapped to the appropriate virtual network. In the case of the pink VTN, as users are authenticated and provided access via the VLAN mapping technique, users are granted access to the NFS server. Below the pink VTN, we have a green virtual tenant network, and as users are mapped via the VLAN mapping technique to that virtual tenant network, they're provided access to the web server. In the next slide, we'll illustrate how the VLAN mapping technique works and additional details of how users are granted access to different virtual tenant networks. Here we'll discuss the VLAN mapping technique in more detail. The VLAN mapping technique is a way for the programmable flow controller to map different hosts into different virtual tenant networks. Imagine in this scenario that customer 1 and customer 2 work for the same company but reside in different departments. As such, customer 1 should only have access to the web server connected to the green VTN, while customer 2 should only have access to the NFS server connected to the pink VTN. When customer 1 is authenticated via Radius, the Radius server allocates a VLAN ID of 12 to customer 1's physical port. When customer 1 sends traffic, it's tagged on the uplink with a VLAN ID of 12 and sent to the OpenFlow network. The programmable flow controller is configured with a VLAN map matching all VLAN ID 12 traffic, and maps it to the green VTN, allowing access to the web server. Similarly, when customer 2 sends traffic, after being authenticated via radius, it's tagged with a VLAN ID of 13. The programmable flow controller is configured with a VLAN map, matching all VLAN ID 13 traffic, and maps it to the pink VTN, allowing access to the NFS server. Next, we'll show you a detailed packet walkthrough so you can understand the authentication steps in this scenario. In this slide, we'll detail the packet walkthrough to show how a user is admitted into the 802.1x and OpenFlow networks. First, when the host connects, the host generates an EAP or PEAP frame containing the user credentials. In step 2, the 802.1x authenticator generates a radius packet and forwards the user's credentials and MAC address to the radius server. Assuming the credentials are accepted by the radius server, the server generates an access accept message that's forwarded back to the 802.1x switch containing the VLAN ID for the physical port for this corporate user. Once the port is allocated to the proper VLAN, the user may then flood a DHCP discover message up to the OpenFlow network. Recall in this scenario that the programmable flow controller is configured as a DHCP relay agent, since the DHCP server resides in the OpenFlow network in a separate subnet than users. Once the relayed unicast packet hits the DHCP server may then offer an IP address back to the client. To illustrate how the programmable flow controller may assist with debug, we're showing the GUI view of this flow in the bottom right. Lastly, once the user has an IP address, they may then access secure resources that reside in the OpenFlow network. In this scenario, we're showing a flow of the user attempting to access a secure server. In the next slide, we'll show the PFC configuration for DHCP relay. Here we'll illustrate the relevant partial VTN configuration for our upcoming demo. We'll highlight how to configure DHCP relay on the programmable flow controller, as well as the VLAN mapping technique as illustrated in our previous slides. First, starting with DHCP relay, notice in the upper left we have a flowless entry matching DHCP broadcast packets. We also have a mirror entry referencing the DHCP flow list. This causes the programmable flow controller to deploy new OpenFlow rules, redirecting DHCP messages to the programmable flow controller. Continuing the DHCP relay configuration, notice in the bottom right under the vRouter we have relevant DHCP relay agent configuration statements. These cause the programmable flow controller to redirect DHCP messages as unicast to the appropriate DHCP server. Moving over to the bottom left, we'll illustrate the VLAN mapping technique. Notice we have a vBridge called VBR0013. This has a VLAN map configured with a VLAN ID of 13. Using this configuration, when the OpenFlow fabric receives a tagged frame with a VLAN ID of 13, it shall be mapped to the VTN called 802.1x demo VTN. In the next slide, we'll highlight a physical topology diagram for this scenario. Here we're showing our physical topology for our upcoming demo. We have two wired clients, one running Windows and one running CentOS, as shown in the lower left. These two devices connect to a Dell PoE switch, which is acting as our 802.1x authenticator. We have an OpenFlow fabric consisting of programmable flow switches configured in a spine leaf representing a campus network. We'll show that each host only has connectivity to the appropriate secure resource represented in the lower right as server 2 and server 3. And with that, we'll get into our demo, where we'll first show the Windows user attempting to access server 2, and second, we'll show the Linux user attempting to access server 3. To start our demo, we'll show a Windows wired client attempting to authenticate to the 802.1x and OpenFlow networks. First, we'll pass incorrect credentials so we can see the authentication fail. We'll attempt to use an unknown username and password of ABC and ABC. As shown here from our Windows host, the authentication has failed. Next, we'll dive into the authentication again, and we'll use a proper username and password. Shown here in our Windows host, we've now properly authenticated via 802.1x. We'll jump over to a command prompt and show that we've received an IP address via DHCP. As shown via this output here, since we have access to the network resources, we can send DHCP requests to the DHCP server. In this scenario, the DHCP server has allocated an IP address of 12.1.1.11. Next, we'll check that we're mapped to the proper virtual tenant network and can access secure resources. In this scenario, this Windows host should have access to a secure server with an IP address of 22.1.1.1. Since we can ping the secure server, the VLAN mapping technique is working properly, and we have access to the proper virtual tenant network. Next, we want to switch to the web GUI so we can see OpenFlow rules and how traffic maps to the physical and virtual networks. We'll jump over to that view now. We switch views, and now we're looking at the web GUI for the programmable flow controller. We'll take a look at OpenFlow rules and how traffic is mapped to the physical and virtual networks. To generate traffic in the background, our Windows wired client is sending a ping test to the secure server. First, let's dive into the physical view of the network. This icon represents our wired Windows client, and the blue lines indicate the physical path that traffic is taking to the secure server. We can see traffic in both directions from client to server and vice versa. Also note that this table lists relevant OpenFlow rules and details to help us debug the path for traffic. For example, we can see ingress and egress ports, as well as the VLAN IDs allocated by radius. In this case, the client receives a VLAN ID of 12. Next, we'll dive into the virtual network view. In this scenario, our Windows wired client is mapped to vBridge 12, and packets are routed over VRT or vRouter to vBridge 22 to the secure server. We can see that flow here. This blue line indicates the path for traffic to the secure server. We can also see the return path from server to client. As you can see, the web GUI provides you multiple ways of viewing both the physical and virtual networks. Next, we'll show you a similar scenario using a Linux host, so you can also see details of how hosts can be mapped to different virtual tenant networks. Let's go dive into that now. In this portion of the demo, we'll show a Linux host connecting to the 802.1x and OpenFlow network. The purpose is twofold. First, we'll show you the Linux client configuration for 802.1x, and second, we'll show how VTNs, or virtual tenant networks, may be used as an additional layer of security by separating hosts into separate virtual networks. First though, let's show you the Linux client configuration for 802.1x. Recall in this scenario, we're using both MAC authentication and 802.1x credentials to authenticate users. As such, the MAC address shown here must be configured in the Radius server. To illustrate, we're also using DHCP to acquire IP addresses. Lastly, in this tab, we'll show the 802.1x configuration for the client. We're using PEAP to exchange credentials. And note, we're skipping some steps to simplify the demo. For example, we're not using certificates to encrypt the exchange of credentials with the Radius server. Lastly, the username in this scenario is Bob. To start this scenario, our ETH1 interface does not have an IP address. Next, we'll enable the network interface to show the 802.1x authentication. As shown here in the right, our host has properly authenticated using 802.1x. Next, we'll show that the DHCP server allocated an IP address to our Linux host. As shown in this output, we've received an IP address of 13.1.1.11 from the DHCP server. Next, we want to verify that this host has access to the proper network resources and is mapped to the proper virtual tenant network. To do so, we'll ping the secure server, which has an IP address of 33.1.1.33. Since the ping succeeds, we know we've been properly mapped using the VLAN mapping technique to the proper virtual tenant network. Recall in the Windows scenario, the secure server had an IP address of 22.1.1.1. To show that the VTNs provide an additional layer of security, we'll attempt to access the secure server as shown in the previous Windows demo. Since the ping fails, we've illustrated that the VTNs provide an additional layer of security since different hosts are mapped to different virtual tenant networks. In this case, the Linux host cannot access the secure server as shown in the Windows demo. Next, we'll show you the Programmable Flow Controller web GUI so you can see the OpenFlow rules over the physical and virtual networks. We switched views, and now we're looking at the web GUI for the Programmable Flow Controller. In this portion of the demo, we'll show how flows are mapped to the physical and virtual networks. To generate traffic, we have a ping test running in the background for a Linux wired host to the secure server. First, let's dive into the physical view of the network. Our icon here shows our Linux client sending traffic to the secure server, as indicated by these blue lines. The blue lines show the physical path for traffic from client to server, and vice versa. These two flows illustrate the traffic from the Linux client to the secure server, and we can see relevant details via OpenFlow, such as the physical ports, as well as the VLAN IDs for the scenario. Next, let's dive into the virtual network. Recall from the PowerPoint slides, we have a VTN configured called 8021x Demo VTN. The virtual network in this scenario involves a virtual router and 3 virtual bridges. This first flow shows the traffic over the virtual network from our Linux wired client to vBridge 13 over the virtual router, and finally delivered to vBridge 33 to the secure server. We can also see the return flow over the virtual network in the opposite path. This concludes our demo illustrating how Windows and Linux users may be integrated with 802.1x and Programmable Flow for enhanced network access control. To recap, in this video we covered different authentication methods available via Radius, use case scenarios or options for DHCP server homing, the network access control implementation details for the wired scenario, as well as a demo of the wired scenario showing the 802.1x and OpenFlow integration for both a Windows and Linux host. We look forward to seeing you in the next video. We'll cover the same options for a wireless scenario.